here is I'm going to tape up. Please tell me I brought scissors. Are supposed to be on this deal. Somebody stole my scissors. If somebody took my scissors, oh, here they are. I was getting ready to say bad things about people not putting things back. Basically what we're going to do here, and I apologize we're not going to get into the relativity like right now, but we will, is I'm going to tape up this end of this thing and not lose every time. Oh God, every time I use this box tape, I always lose the end. It takes forever to find the ending. Okay, I'm going to tape up this end. If you remember, this is what I tell the young kids coming through. Everyone take a look at your thumbnail. And how many pounds per square inch of air is bouncing off and causing pressure on your thumbnail right now? Do you know? What? About 14. Yeah. So, just on your little thumbnail, there's 14 pounds of pressure per square inch. So if you take your thumbnail and put it all over your body, you know, that's like a bowling ball. So it's like 80,000 pounds is smushing on you right now. Any of you remember the old movie 2001: A Space Odyssey? There's a scene where he goes through a vapor lock where there's like no, he runs through a vacuum to get back on board the ship. He's actually out in outer space without a suit on, and he goes and runs and gets back on the ship. Well, he would have exploded instantly upon hitting zero, you know, with no air pressure whatsoever. His whole body, all his body cavities would have just, you know. Which was also a great scene in a James Bond movie, where James Bond put some kind of gas propellant thing in the bad guy's mouth and he blew up. But anyway, so what we're going to do, we'll put this in here, put this ping pong ball. This is what I'm going to have to ask Brittany and Catherine and David. Well, not yet. Everything's safe right now. Yeah, this takes a while to set up. I'll teach you about relativity in about 15 minutes. Takes 15 minutes. What do I do with the tape? Do y'all see it? Oh, here it is. All right. Now I got to tape up the other end. I lost it. I hope this doesn't. Yeah, it'll be okay. We're just going to do this once because it takes so long to set up each time. Anyway, I had the Girl Scouts in last week. 6 hours of teaching Girl Scouts physics because there were 6 different groups and they each had an hour and a half or something like that. It was somewhat painful, but it was actually very fun. We did this, and with one group it didn't work. And the whole reason I'm taking up all this time is we wanted a video of this. So for the department, I think that's a pretty good seal on that end. Okay, now what's going to happen is this. We are going to set this thing up like this. And then put this one right here like this. And then I'm going to plug it in. All right. Now, where's my firing pin? Brought it in. I swear to God I had it. What'd I do with it? Son of a gun. It's with my key. Yeah, that's what I'm looking for. Thank you. This is annoying. All right, now, Thomas, Brittany, David, go kind of mingle back there. I think everybody else will be pretty safe. I'm going to go ahead and lock the door so that nobody can get in, if I can. Because basically, once I fire this thing up, what I'm going to do is I'm going to suck all the air. This is just a piece of PVC pipe, okay, and a ping pong ball inside it. And what I'm going to do is suck all the air out of the PVC pipe. PVC pipe works good because it's very rigid and it doesn't collapse. And then, once I get all the air sucked out and I've created a complete vacuum, I'm going to poke a small hole in the bottom of, in the back end of this thing. And it's going to send this ping pong ball shooting out through that end at close to supersonic speed, actually. Because you're going to get 14 pounds per square inch instantly on this little bitty ping pong ball. So it's whew. And we've calculated it down to, well, it's probably close to the speed of sound. Okay, oops. All right, we'll let Jonathan in. You're just downrange. The old Marine in me, range safety officer, came out. All right, ready on the left, ready on the right, all ready on the firing line. You may commence firing when your dog targets appear. All right, so here we go. Now we're going to suck the air out. That's this little vacuum. That's all it is. And there's a little pop to this, so if you want to cover your ears, Catherine. Oh my gosh. All right, come on in. Hurry, hurry, hurry. I'm glad I had that locked. All right, now all the air's sucked out because it's not making any noise, so here we go. Yes! It worked! Yay! What happened to my ping pong ball?
It exploded. I don't know.
It didn't even come out!
That was just the air.
It was just the air that blasted that. Well, you saw the air. What's that? Yeah. Well, that was bootsy. Why didn't it come out? Oh, well. All right, best laid plans. Let's learn that really. There we go. You saw the thing. Okay, ping pong ball bounced around and shot the thing. We're going to have to get a video of this after class. We're going to try it again, okay? All right. Shoot. See? The ping pong ball got stuck to the thing. All right. Well, anyway, let's go on to relativity here. Let me get this out of the way. Well, that was a good bolt of air that knocked the cans out of the way. All right. Darn. Now, I've told you this is lend credence to that saying, you know about the three sciences, right? If it's biology, it's gooey. If it stinks, it's chemistry. If it doesn't work, it's physics. So we just kind of ran into the physics thing there. It didn't work. We'll try harder next time. All right. Usually get a ping pong ball, smashes the can, but not this time. Okay. All right. And we'll set this up later. Okay. Now, Wednesday, we're taking our little take-home test. You're free to come back, Brittany and Thomas, if you want to get back to your stuff, but or David. Give me a second, and I'm going to set up the and we'll talk about relativity. All right, the first thing on relativity is this, that you kind of need to get your head around. This is special relativity. First of all, we are not going to be talking about acceleration, all right? If you, let's say you're on a bullet train, okay, that's going at a constant velocity, and it's such a smooth ride, such a smooth ride, you feel no jiggling, no nothing, and the shades are pulled and it's completely dark. Can you tell you're moving? No, you can't. So you're in an inertial, that's called an inertial reference frame. Okay? You're in the XYZ inertial reference frame is XYZ coordinates with good old time thrown in there. Einstein added, said time changes just like, you know, we have no problem with distance changing, X and Y, and stretching, contracting, and all that, or Z, but we have a real problem with time stretching and contracting. And as you saw on that little video I showed you on Monday, they had the tarp, and it showed that how the time kind of stretches around heavy mass planets and stuff like that. But here's what you got to get around your head. Let's say Catherine and I are playing catch, okay? All right? She's the quarterback, and I'm the receiver, and I do a button hook. She throws me the football at 15 meters per second, and I run back towards it at, I was going to say 10 meters per second. That'd be put me up there with Usain Bolt. I don't think so. Anyway, okay, so she throws a football at me at 15 meters per second. I run towards it at 7 meters per second. How fast is that football coming at me? Exactly. It's coming at me at 22 meters per second, right? So she goes 15 meters per second this way. I'm running at it this way at 7 meters per second. Relative velocity. The velocity of the ball relative to me, all right, velocity of the ball relative to me would be 22 meters per second. All right? Now, here's the other weird thing. Yeah, I didn't want a velocity of a BM. I had no idea what that would be, all right, for you pre-metters. But anyway, this is being broadcast to millions out there. I hope you all know. I'm in trouble. All right. That's all I need is the FCC to get on me. All right. So here's the deal. Let's say now Catherine and I are playing Einsteinian football, okay? Which basically means there are no more ex-jock commentators. No. Anyway, what we've got is she's going to throw me a football. The velocity of the ball is going to be, let's say 0.7 c. Get used to seeing that while we're doing relativity. 0.7. In other words, 70% of the speed of sound. Okay? Whoops! I forgot to unlock the doors. My apologies. My apologies. We did an experiment. I didn't want anybody walking in and getting killed. So, there we go. All right. 0.7 b. And then I'm coming back at her. I'm coming back. I'm going to go this way. My velocity of me now is going to equal 0.6 c. Now, what's the velocity between the two of us? The relative velocity. From what you said, what would Newton say it is? 1.3 c. The velocity of the ball relative to me is now equal to 1.3 c. Wrong. Wrong, wrong, wrong. Can't do that. Can't do that according to Uncle Albert, okay? He said, nope. Here's postulate, special relativity postulate number 2. Relativity postulate 2 says this. C and only C. Nothing exceeds the speed of light. Nothing goes faster than the speed of light. So, you know that old riddle? In fact, Einstein thought about it for a long time. I don't know if he thought about it in this terms. There's the old riddle, if you're on some kind of cosmic motorcycle, going the speed of light or close to it, and you turn on the lights, turn on the headlight, what happens? Well, those photons move at the speed of light too. Okay? And somebody seeing those photons, it's going to be the speed of light. It's coming at them. All right? Okay. So, how do we get there? Well, it's weird. okay? The world of, it's all relative velocities, and everything is fine. Everything is fine. Good old Newtonian physics works just fine as long as the velocities are slow. And I mean it's slow like around 20% of the speed of light. Nothing really, and I can't think of anything besides stars and stuff like that that move anywhere near the speed of light, especially nothing here on Earth moves at 20% the speed of light. You know, the fastest things we can think of are, well, we do make things go that fast here at those big electron accelerators things. They go around, they go about 0.9999999 this speed of light. And what they're doing is they're running around, they're going around and they're smacking into each other. Hopefully we get a good collision, and then they take all these measurements off what happens from that collision, and that kind of leads us back to the Big Bang thing. Okay, which I'm going to show you a video on that tomorrow real quick before you take your in-class test, which will be relatively easy. Okay, but now, so because, and here's the other thing too. Postulate number 1 says this: all of the laws of physics, good old laws of physics, Newtonian laws of physics, apply in a reference frame. Okay, so the laws of physics still apply in a reference frame, and if you do experiments, you will get the same answer as somebody else doing the same experiment somewhere else in their reference frame. Okay, the laws of physics apply. That's postulate number 1. Postulate number 2, nothing exceeds the speed of light. That gets us into a conundrum, though, with, now we're going to get into that whole thing of time dilation and length contraction. Okay, we're going to get into that whole thing of time dilation and length contraction, and the slides do a much better job of it than I do. So we're going to go into the slides here. I've kind of given you the background. Now we'll get into the slides, and we'll talk about chapter 28. Okay. We probably need to turn on everything here. Wow. Only got 35 minutes to cover this whole chapter. We got it. We can do it. We can do it. Because it's an open book test, and you'll have time to, because there's some neat things that we got to do. We got to look at time dilation, length contraction. We'll look a little bit at the relativity, I mean at the momentum, relative momentum, and we will look wholeheartedly at energy, and then relative velocities. How did he come up with that silliness of one thing? Okay, an event is a physical happening that occurs at a certain place in time. Okay, to record the event, each observer uses reference frame. We've already talked about that, and in my words, it works just as well. Okay. All right, an inertial reference frame is where Newton's law of inertia is valid. Newton's law of inertia says an object what? At rest will stay at rest unless acted upon by an external force. Okay? Or an object in motion will stay in motion unless acted upon by an external force. And it all gets into the thing where it's perfectly valid to say, if I'm traveling east at 70 miles an hour through the cornfields of Iowa, or north through the cornfields of Iowa, what's to say that the corn is not traveling south at 70 miles an hour and I'm stationary? Okay? It's all relative. Okay? The reference frame is my car. I'm in my car's reference frame as long as I'm going at a constant velocity. Once you throw in acceleration, that's when you get into general relativity. And then that gets way hard. Okay? But not too bad. Okay. All right. So here's an example of two events, of one event by two different observers. Okay? Looking at the event. All right. Now, let's get into, here's the two. The laws of physics are the same in every inertial reference frame. This is just saying the speed of light is the speed of light is the speed of light. Okay? And nothing can go greater than that. All right. Now, And here's what I was talking about when Catherine and I were playing catch with the football. And then all of a sudden we went to playing catch with intergalactic cruisers and stuff like that, shooting laser beams at each other. Oh my goodness. Photon beams. Wow. Okay. By the way, Comic-Con is going on in San Diego right now. If y'all know about what Comic-Con is. Okay. There's a few nodding your heads. You all need to be physics minors, I'm telling you. Okay, now, here we go. We're going to look at this light clock so we can first talk about light dilation. Okay? A light clock, and we're going to talk about light dilation. We're not going to the eye doctor. Time dilation. Time dilation, we're going to stretch time. We're going to stretch it out. Okay? All right. So here's our little clock. It goes ding, ding, ding. It shoots it up and comes back. We're going to call that 1 second. Okay? It might be, it's actually probably a billionth of a millionth of a second, but we're going to call it 1 second. Boom, boom. All right? Now, if I had that clock sitting next to me, it'd just be going like this. Ding, 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 right? Okay? Now then, I'm going to put that clock on a spaceship. Okay? I'm going to put that clock on the spaceship. And the astronaut, I'm on the spaceship, I'm just seeing that clock going do, 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 do. So it's just keeping nice little time. It's keeping great time. Okay? In the interim, there's an observer watching me go whooshing by. All right? And as I go whooshing by on the spaceship, she sees that clock go ding, doing, ding. Then it finally hits the detector. Okay? So my little ding ding is her ding, doing, ding. Okay? There you go. There's time dilation right there. All right? And so, because the light pulse had to travel a greater distance between ticks. Okay? So therefore, if it's going the speed of light, it's got to go. It's got to take longer time because nothing exceeds the speed of light. That's the constant. So therefore, since it's going the speed of light and it took longer, or it covered a greater distance, obviously it took longer. So her elapse, so what she sees me go whizzing by might have been, I went whizzing by in 1 second as far as I'm concerned. She saw 2.6 seconds, depending on my speed. Now remember, we both had the same relative speed to each other. I just happened to be going this way at 0.75, 75% the speed of light. That's what she sees, but I see her whizzing back that way at 0.75 speed of light. Okay? So the point, whenever you see the velocity, that's going to be the same in both, for both people. All right? So, delta TO, get this in your brain, this is a good thing to know, is called, delta TO is the proper time. All right? Delta TO is the proper time. Delta T is the dilated time. All right? So here's the deal. If I'm traveling in this spaceship, zipping towards Alpha Centauri at 0.92 the speed of light, because we've got a new spaceship, you know, like that's where Swiss Family Robinson was going, remember? Y'all don't remember. Well, anyway, in Lost in Space, and it's because Dr. Zachary Smith was a stowaway, knocked him off course, and they could never get home again, and so we're stuck with Penny and her Chim Chim, and they're, oh well, I've got off track here. But anyway, so, and anyway, as far as I'm concerned, I'm going to get there in no time. I'm going to get to Alpha Centauri in about 1.5 years, but somebody on the ground sees me. It took me 4.3 years to get there. Yet, okay, I'm going to bring back another old movie. Did y'all ever see Close Encounters of the Third Kind? Anybody seen that? Oh my God, some of you have. All right, there's a big scene, the Devil's Tower in Wyoming, and the alien spaceship comes in, whatever, and lets off the pilots who got sucked up in the Bermuda Triangle during World War II, and they get off and they're the same age, you know, they haven't aged at all, because they've been zipping around with the aliens at the speed of light. So their little clock is just going ding, 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 ding. okay? And those of us on Earth observing them, our age has elapsed quite a bit. That's what they were talking about in that movie. All right, I got to come up with some more recent movies in 1978, I can tell. All right. Okay. Now, so that's time dilation. Here's the formula for it. There was a derivation in the book, but last week at summer school, we don't do derivations. We just explain what's going on and slap the formula up there for you. Okay? This is the proper time. This is the time, the proper time, delta TO, is where the clock is not moving. The proper time is usually with the person moving. Okay? It sounds like I just contradicted myself. Actually, I didn't. Because as far as the astronaut's concerned, that clock, the two events, the events that we're observing is this light going doink, doink. This observer seeing that event on my plane, on my spaceship, saw a much different thing. So it'll take much longer. Okay. So with that in mind, okay, and then the time dilated, that's usually what an observer sees. So, when you're doing your homework, or when you get your take-home test, or not take-home test, but when you're working together tomorrow, and it says like a pion or something like that, that's one of your homework problems. I won't give you the Klingon problem. I'll probably give you problem number 3, just let you know, so you can get it all ready to go, and you can just turn it in and be gone tomorrow. All right. Anyway, or Wednesday. If it says the observer, he's seeing the dilated time. The actual person writing on that pion when you're doing your homework is delta T naught. Okay? All right. So that's time dilation. Okay. Now then, so this is what they give. The spacecraft is moving past the Earth at the constant speed. The astronaut measures time interval to be 1 second. No biggie. What is the time interval that an Earth observer measures? So what's delta T naught? I think they give you the calculation here. Yeah. You get 1 second. Now then, get used to this 0.992 over C. I'm going to write this over here real quick. Here in relativity world, get used to this little guy. He shows up all the time. But we'll always give you that V is like in some percentage of the speed of light, okay? And so basically you can just go 1 minus 0.7 squared, because when I square him, I get 0.7 squared C squared divided by C squared. Whoosh, those cancel. So it makes it much easier when you don't be punching in 3.0 times 10 to the 8th squared on your calculator all the time. All right, some of them will, because it'll go nuts. All right, and this is in the square root. All right. Okay, now, since we know this, all right, so this observer sees, all right, so he's taken off to Alpha Centauri. Okay, cool. So let's just keep this idea over here. I know I'm not supposed to film both places, but this is the last class. I can do what I want. We're okay? All right, good. All right. So now, but look what happens. The observer, ground observer, goes, hey, Alpha Centauri is 4.3 light years, LY, away. That's a distance. Okay? He's going, hey, you're 4.3 light years away. But wait a minute. I'm on this little spaceship. Okay? I'm on this little spaceship. I'm going 0.92. In other words, LO is actually equal to the observed proper length. LO is called proper. We're getting into length contraction now. The proper length. Hey, I measured the Alpha Centauri. If you're traveling at 0.92 C, in other words, it's going to be 0.92 C times the dilated time. times the delta t. So that length that I observe, being stationary, I'm the stationary person measuring that length to Alpha Centauri, okay, is, hey, it's a lot longer. I've got it as 4.6 light years or something like that, okay? So I've got it as like 4.3 light years away. You're a long ways away. However, the contracted length, now we're going to talk about contracted length here. The contracted length, hey, me and my spaceship, all right, I'll agree with my velocity is 0.92 c, but hey, my time is only 1.4 light years. Okay? My time is only 1.4 light years. So it's much shorter. Much, much shorter. All right? So we'll get to that idea right now. Here we go. I probably should have been doing this all semester. Working over there, having this thing over here. Okay, proper time interval. The proper time interval between events is the time interval measured by an observer who is at rest relative to the events. So the event that we were measuring was that light ray going doing, doing, okay? And he's stationary because he's standing right next to it. The dilated time, okay, now we're going to talk about length contraction, which is what we just talked about over there. And here's the formula for it. All right? So in other words, I've got the proper length here as an observer on Alpha Centauri, but my spaceship goes zipping past, and notice how everything's smushed. Everything's contracted and smushed. So length contraction is equal to the proper length times this relativistic factor here, is what I'll just call that because it shows up all the time. It's both in time dilation and length contraction. Okay? So when you're working the problems, if it says the observer sees a time, that's delta t. But if an observer takes a measurement, that's L naught. Okay? All right? Just get the wording down for how the problems are worded in relativity. Okay? So, but let's say I've got, for like your homework, you've got, it says that someone in a lab observes a pion has a lifespan of so long. Well, a pion is actually moving through the atmosphere very fast, and they see that, and they measure that time. That would be delta t. But someone writing, some mythical person who's smaller, say some quark riding this pion, okay, like a seahorse, I guess, that would be delta t naught, however long that trip lasted him, okay? But the actual length, but the observed length is the one by the observer. Okay, so there we go. All right. So an astronaut using a meter stick that is at rest relative to a cylindrical aircraft measures the length and diameter to be 82 meters and 21 meters respectively. Okay? So when he that's a proper length. That's L naught. The spacecraft moves with a constant speed of 0.95 c relative to the Earth. What are the dimensions of the spacecraft as measured by an observer on Earth? Okay. Wait a minute. All right. Hopefully they have the answer. Let's take a look. Yes. Okay, good. Whew. Whew, 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 whew. All right. Everything I said was good. All right, good. Good. So he's at rest. He takes the measurement. Boom. He's got it. L naught. So L naught is 82. Notice it only contracts relative to the direction of the velocity. Okay. So if I'm going along the x-axis, I'll only contract along the x-axis. So I get smushed. All right. I don't get contracted this way. Now, if all of you sudden you take off in the XY plane at a 45-degree angle, then both things are going to get contracted. Okay, because you're moving relatively fast. Okay, so that works. That's good. Okay, now diameter stays the same. Okay, now let's talk about relativistic momentum, and then we'll get to the real. Wow. So are you all getting this? Kind of. It kind of takes a while to get your head around. Yes.
So you have the compression or dilation of time. What happens when that thing in motion stops? Are they now on different times, or does the time catch up? Are they the same?
Time doesn't catch up. I mean, time continues on.
It seems like you're not actually losing time. You're just perceiving a loss of time or a change of time.
No, it's all relative to what you're observing, to where you are, So that person, his reality is, things are perceptions. It's all. His reality is 1.4 light years to get to Alpha Centauri. Our reality from where we are is 4.6 years. And it's not like he's now there and waits another 3 years. Now 7.6 years is elapsed for us, and it's only 4.6 for him. Now he comes back, all right? And he's going to be zinging back, taking 1.4 years, according to him, to get back.
So he's like 6 years younger than.
Yeah, right. It's kind of weird. Yeah. It's like, whoa. All right. Now, relativistic momentum. See, here's what I was talking about. All of a sudden, because of this, what I call this relativity factor, okay, the new P. Now notice, at good old Newtonian speeds of 20 meters per second compared to 3.0 times 10 to the 8th meters per second, 0. All right, so that's why in first semester, or most things here on Earth are fine. However, GPS systems have to be accurate up to a factor of 10 to the 13th, okay, like 0.00001, all right? And they have to, since they're cruising about at 4,000 meters per second around the equator, they have to take into account relativistic changes. Otherwise, you'll wind up, you'd want to go to UMKC, you're going to wind up in Kearney, right? That wouldn't be good. Nobody wants to go to Kearney. No, I'm kidding. Kearney's actually a nice little town. It used to be. It's gotten too big now. But anyway, it's got an amphitheater, though, and it brings back old dead hair bands, and stuff like that, so it's good. Pantera will probably be there next summer. Slayer. Anyway, all those bands that were huge during Desert Storm when you all were in kindergarten. All right, now, so as you see, the relativistic momentum here, as you see, as we're down here around 0.2 c, it's still relative. It's still okay. But then once we start getting close to the speed of light, relativistic momentum increases tremendously compared to good old Newtonian momentum here, because this guy's getting 1 minus v. This guy's getting closer and closer to 1. All right. And when he gets to 1, this thing goes to infinity. All right, so that's relativistic momentum. I didn't give you any questions on that, and I won't give you any questions on that other thing. I just wanted you to see the difference here. Now for 2 semesters, we're coming up to the greatest equation of all time because it's so elegant and so simple. Here we go. Dun-da-da-da. There it is. Now, the total energy of an object is the weird thing. Mass and energy are related to each other. Can pretty much be the same thing. If I lose mass, I lose energy. If I gain mass, I'm gaining energy. Okay? So let's look at this total energy of an object. The total energy of an object. That's an object moving along. Okay? That's an object moving along. Now notice what happens. My energy goes to infinity if I approach the speed of light. Okay? Therefore, my mass goes to infinity as I approach the speed of light. All right? Which, you can get into all these weird conundrums, just like Kurt brought up. People have different realities. Nothing in the law of physics says we can't go back in time. It's just that my reality doesn't allow for that to happen. Because then I could undo a bunch of, I would make it. Boy, can you imagine? I didn't mean to say that. Anyway. So. All right. So, rest energy of an object. So in other words, what we're going to do, I think, on the next slide here, E equals mc squared. That's the rest energy. This is pretty much telling us that the energy of an object is directly related to its mass, which led us to things that go boom. Okay. Because if we can unleash the okay, the sun's losing mass. I'd like to pause here and take a look at the example. And I also want to pause here because I think, and I'm going to go ahead, what does this mean to you? I'm going to go ahead and look at, I think, one of your homework problems, problem 25. Because you're going to go, what? How? I mean, the first time you read it, you're going to say, well, what does that have to do with the price of tea in China, as my mother used to say. But anyway, along with, if all your friends jumped off a bridge, would you? But anyway, here we go. 4 kilograms of water are heated from room temperature at 20 degrees Celsius. So let's just do this problem over here. Since I got the okay that it's okay to shoot over here, we'll shoot over here. So here we go. Let's say we got this. I got a mass of 4 kilograms of water. Okay? And I'm going to heat it. My delta T is going to be 40 degrees Celsius because I'm heating it from 20 degrees Celsius to 60. Okay? How much energy does that take? Remember? Thermo people, chemists, chemistry folks? What's specific heat of water? Huh? 4187. You're not in chemistry class. You're in physics class. We're doing joules. No, just kidding. Joules per whatever, All right, so specific heat of water, C of water, is equal to 4187 joules per kilogram per delta T, per degree Celsius, something like that. Yeah. Okay. So, okay. So we can. So that's the change in temperature. It doesn't matter if it's kelvins or Celsius when you're doing a change. All right. So the amount of energy that this requires, as you recall, was Q equals 4 times 4187 times 40. Okay. I brought my trusty calculator today. So at least I think I did. I'm having trouble with firing pins and everything else. Ping pong balls, firing pins. Typical physics day. 4187 times 40. That's about 6 million. That's about 6.69 times 10 to the 1, 2, 3, 4, 6 joules. Okay? Now then, what's the change in mass? So that'd be the next question. That's the next question is, well, okay. Well, what's the change in mass of the thing? Aha! Well, this is a change in energy, right? So the change in mass, the change in energy equals Q, and the change in energy equals the change in mass times c squared, which equals Q. And so the change in mass equals Q over C squared. So it's not going to be much, because I got 10 to the 6 here divided by 9 times 10 to the 16. Okay? Which we can, let's round a factor of 10. Since we're at 9, let's just go one more higher. Let's say it's 1 times 10 to the 15 divided by that. So you get 10 to the negative 9 grams. Not too much. Okay. Yeah, definitely. Definitely. It's not the specific heat of water. Right. See, the trouble is we only have 26 letters in our alphabet, and we've got all this physical phenomenon that has all these different... Right. Yeah. Well, we let the biologists mess with the Latin, so, which is good when you're naming all that stuff. Okay. So anyway, like here, since the sun radiates, this one's already worked out. The sun radiates electromagnetic energy at a rate of 3.92 times 10 to the 26 watts. Wow. So that's how many joules per second. That's joules per second shooting out there. What is the change in the sun's mass during each second? Oh, good, they gave us each second. So if we multiply this by 1 second, that's the number of joules that we get. Okay? And so we say, all right, well, we'll say the change in E is equal to those joules of 3.92 times 10 to the 26 divided by 3.0 times 10 to the 8 squared, and we wind up with a huge mass that the sun loses each second, and then we'd multiply that by how many seconds are in a year, or in 75 years, and the sun is losing, in our lifetime, is going to lose 4.36 times 10 to the 9th kilograms of mass. Boy, I hope it doesn't burn up, lose all its mass. But if you take that in comparison to its actual, to the actual mass of the sun, this little bit here, you get, it's only, in 75 years, it's only going to lose 5 times 10 to the negative 12th. Yeah, and this is how much it loses in 75 years. Right, this is how much it loses in a second. Wow, that's a lot in a second. 75 years, this is going to lose a bunch more. Almost the mass of the Earth, but it's got, no, not quite the mass of the Earth, about half. No, not even half. 500, thousands. Okay. So it's just a matter of taking that. Now, let's get to the real fun part. The real fun part. The last part. Okay, so we know that Einstein gave us that mass and energy are, in other words, if I lose mass, I lose energy. If I gain energy, I gain some mass. Those kinds of things. So they're logically equivalent to each other. Now, for the last thing, for that one, well, here's a massless spring. Is there such a thing as a massless spring? Only in physics 1, but and in advanced mechanics and stuff like that, because we want to keep things simple, but or simpler. There's no such thing as keeping any of this simple. But since that's got a potential energy to it, when we stretch or compress, yeah, that spring's going to change mass. It's going to change mass a little bit because there's energy being added. When we compress a spring, we're adding energy to it. Okay? It's gaining potential. It's getting ready to do something. I know a lot of physicists don't like it when I say that, but that's the way I always view potential energy. It's got the potential to do something. Like if I raise something up, it's got the potential, if I drop it, to gain kinetic energy as it falls. Those kinds of things. So it's raising its energy here, and it's raising its energy there, so it would be increasing its mass. Now, here's the deal. Here's what I was talking about when Catherine and I were playing football. All right? It's all a matter, all of these relativistic addition of velocities, all of these things depend upon the subscripts. Subscripts are huge. And how we do this. So we got the velocity of the ball relative to the truck, the velocity of the truck relative to the ground, and then the velocity of the ball relative to the ground. Then see how these two T's kind of cross out and you got VBG there? Okay? That's what we're going to do. And here's the key to it. Here's the key to working these problems. And I'll work an example. I'll work a couple examples of this because this one's kind of screwy. I think for the most part you've kind of grasped what we've done up to this point. But here's the key to it. If you change subscripts, like if I change, all of a sudden the velocity of the ball relative to the truck is 8 meters per second, positive. What is the velocity of the truck relative to the ball? Now all of a sudden we're letting the ball be stationary. So what's happening to the truck? It's shooting back that way at 8 meters per second, so it's negative. So if you flip-flop the subscripts, you got to change the sign. Okay? Flip-flopping the subscripts means changing the sign. All right? Because when you flip-flop the subscripts, that's like, okay, now the corn's moving past me at 70 miles an hour. I'm not moving past the corn at 70. I'm stationary. And it's the corn moving, okay, going the negative way. All right? Okay, so let's do an example of these kinds of problems because you've got a, let's just do your homework problem. That'll be fun. We did your homework problem here. So if your numbers will be different, it'll give you like 3.97 kilograms or something silly. It'll pull a Wiley plus on you, I guarantee. Just to be annoying. Okay. Here we go. So let's take a look at, here we go, a spacecraft approaching Earth launches an exploration vehicle. Okay, so I'm going to have, I've got a spacecraft, so I got a C, so I got a velocity. So here we go. I'm making no sense. Here I am, standing on the Earth. Whenever I do these problems, I always think of French class. You know why? What do they make you read in French class, no matter where you take French? The Little Prince, right? This always reminds me of the cover of The Little Prince. But anyway, all right. So we've got the velocity of the craft relative to the Earth equals 0.5 c. Half the speed of light. Okay? Now, this spacecraft, what this spacecraft does, this little spacecraft here, okay? A little Martian in it, okay? What the spacecraft does is it launches a little explorer thing. All right? And I observe the velocity of this little explorer in relation to the, well, let's call it the shuttle, in relationship to the Earth, is equal to 0.7 c. Okay? Now then, the question is this. What is the speed of the shuttle relative to the spaceship? Okay, what's the speed of him relative to him? So what we want is we want the velocity of S to C. That's what we're asking. Okay? So here's what we do. We got to line up the subscripts. Okay? So we're going to line up the subscripts here. We're going to do this. We're going to say, all right, the velocity of S to C is equal to the velocity of SE plus the velocity of EC. So what did I do here? I changed the subscript, so therefore this is going to equal 0.7c plus negative 0.5c. And it equals 0.2c. And you're going, wait a minute, that's Newton's answer. Right, we forgot something. We've got to add this little guy down here. Divided by 1 plus, because the actual formula for finding the relative velocity is going to be this. It's VSC plus VEC over 1 plus VSE times VEC divided by the speed of light squared. Okay? So once again, you're going to get 0.7 times 0.5 times negative 0.5 c squared. The c squareds are going to cancel. So this is divided by 1 plus negative 0.5. Whoops. Negative 0.5 times 0.7, which would be 2c over 1 plus, that's 0.35 negative 0.65. Oh, and the c's are gone. It's just a factor. It just comes up with a factor. So I end up with 0.2c over 0.65c, and that is 0.31c. Okay, let's try one more of those. And then for those of you that are interested, we're going to try and do the canon one more time, but the rest of you, if you say, okay, we believe you that it works. Because it really does. It works. It's pretty cool. But I got to set that up again so that our illustrious filming crew on location can do it, can get a film of it. All right. Oh, by the way, I've got tests that I need to pass back to some of you all too. So I'll get that started too. All right, let's try another one. Let's do the Catherine and I playing football problem again. Okay? Remember, she was coming at me. She threw a football at me at 0.7 c. That's the velocity of the football relative to me. Well, she's an observer. She's going to be an observer down here. Here's Catherine down here. I just moved her from here over to here. She's still seeing the same thing. Okay, so it doesn't matter. So I've changed her from here. So she's throwing the football. This is the football relative to the Earth. And then here I'm coming back, button hook back at 0.5 c with me relative to the Earth. What we wanted to find was this. What we wanted to find was, and we came up with 1.2 earlier, and we found, we go, oh, Robert wouldn't allow that. What we want to find is the velocity of the football relative to me. That's what I want. Notice I've changed my subscripts. So what I do is, I go, okay, I got VFE plus, now, this guy's actually negative because he's coming this way right now, right? But when I change him, I got to get VEM. He's going to be positive over 1 plus VFE over VEM divided by c squared. So this will be 0.7 c plus 0.5 c, which is what we got earlier, which was our 1.2, but we forgot about this guy. 1 plus 0.7 times 0.5 over c squared, and this is c squared here, so those cancel, and we get 1.2c divided by 1.35. Notice it's less than c. And in fact, you can do this all day long. You could have, let's have two things coming at each other at the speed of light. This is the culmination activity. All right, so we've got the velocity. Now Catherine really throws a football at me. At C, I really can do a button hook. I'm coming running back at her. Velocity of me to Earth is equal to c. So when I put these in, I'm going to get c plus, oh, this is negative. Plus c over 1 plus c squared over c squared. So I wind up with 2c over 2. Uncle Albert didn't let us down. We're not going to exceed the speed of light. And by the way, it's been proved by experiment. Okay? So until you get it into a lab, and in this case the lab happened to be, is actually worked a little bit backwards. Remember we talked about Michelson and his study of the wavelengths of light and all that stuff in the 1880s, 1890s. He actually showed that speed of light's the speed of light. He just didn't come up with the theory behind it. So sometimes the actual precedes the, okay, now we've got to have a theory that sticks with this. And that's kind of the way quantum came about, because things were happening weird at the microscopic level, or way down at the subatomic level. Okay, that's it. That's it. I'll see you on Wednesday. It'll be 5 or 6 questions. Relativity. There'll be a thin film, guaranteed thin film problem. There'll be one mirror with 2 lenses. Not a mirror, but 2 lens, thin lens problems. Okay, there'll be one of Eddie. Okay. All right. We've tried this at the beginning of the hour. Now we're going to try it here after everyone's left. These equations on the board have nothing to do with it. These are relativistic equations. This will not go at the speed of light, but it will go close to the speed of sound. We're going to suck all the, I've got a ping pong ball inside this PVC pipe, and I'm going to suck all the air out of this thing. And then I'll take this nail, punch a hole at this end of the, in the tape, and what's going to happen is we're going to get 14 pounds per square inch rushing in close to the speed of sound, because molecules in the air bounce around at close to the speed of sound, and so that's where they're going. That's why they're going close to the speed of sound. They'll smack into that ping pong ball with much more mass than the ping pong ball and send it soaring. Hopefully, suck all the air out. Takes a while. We've got to wait for it to quit gurgling. All right. Now that we've quit gurgling, I think we've got a good seal. We'll let it. There we go. That worked well. Beautiful. Beautiful. Don't turn off the camera just yet. Let's take evidence of the ping pong ball. Oh my gosh. I just got hung up. Thank you. That worked. Where'd the ping pong ball? Oh, here it is. Ping pong ball got a little dent in it, but nothing like that point in the center, which took the brunt of the ping pong ball traveling close to the speed of sound. Thank you. I'm glad it worked. Okay, you can kill it now. Good.